Okay, good evening and welcome to the North Jersey Astronomical Group's April meeting. And tonight we're going to have a presentation by one of our members. And then for the club members, please do stick around for our business meeting, which will follow immediately afterwards. And so stay tuned for that. For those of you who are visiting us, our astronomy club usually meets at Montclair State, and hopefully we will, sometime in the near future, begin our in-person meetings once again at Montclair State. And so keep an eye on that. Our website is njastro.org, and that's where our events are posted. Hopefully we'll also be able to resume our in-person telescope nights at Montclair State as well. And we have a date picked out for this week, actually, but looks like the weather is not going to be too good on Thursday night. So we usually do those events. And so far, the weather does not look very good. So we'll probably likely have to postpone that. Coming up in May, though, we're looking at a nice lunar eclipse coming up here in New Jersey. And so hopefully we can finalize the arrangements for that. We've got a site picked out where we can go and have a public viewing of the lunar eclipse on, I think it's May 15th, if I remember correctly. And so keep an eye out for that on our Facebook page and our web page. So do check that out when you have a chance. We're going to begin our program for this evening. Our guest speaker is one of our own, the Vice President of the North Jersey Astronomical Group, Chris Morrow, is going to talk about something that's been in the news lately, Lagrange Points. And if you don't know what those are, well, I'm sure Chris will explain all about that. So Chris, if you want to take it away, put up your PowerPoint, we'll get started here.
Okay. Here we go. Okay.
Good.
Good evening and welcome to tonight's presentation on Lagrange Points. Before I start, I'd like to thank Kevin Kennard, president of NJAG. His presentation on the Webb telescope was the impetus behind this presentation, and so that's why we're doing it. I also like to thank Dr. Mary Lou West. She continues to provide guidance and support and encouragement for all the presentations. And I'd also like to thank a lifelong friend of mine, John Fahey. His knowledge of history and events, he was able to help me put the life and times of Lagrange into a historical perspective, which is important. So the recent launch of the Webb telescope brought to the attention of people Lagrange points. The Webb telescope is orbiting around the L2 point. But the question was, well, what are these points? Why are they there? How do they behave? And how are we using them? So the presentation will answer all those questions and explore the life of Joseph Louis Lagrange. I was first introduced to the work of Lagrange as an undergraduate. I was studying computer science, and one of the topics was mathematical optimization. So I used to know how to solve all these equations, by the way. I can't do that now. But basically, you have constraints on a function, and you can identify maximum and minimum points. So usually where Lagrange multipliers and Lagrange functions lead is to a saddle point in the shape of the curve. There are close to 50 different concepts and equations and theories that have been named for Lagrange that he developed. He was quite prolific, and a scientist who covered numerous areas. So these are some of them. In number theory, the sum of four squares, where every positive integer can be expressed as the sum of four different squares. In the optimization, it was the Lagrange multipliers. Differential equations, the Euler-Lagrange equation. Set theory, he identified groups and subgroups and group symmetry before Galois had even codified his set theory tenets. In linear algebra, reduction to quadratic forms so they could be solved. In numerical analysis, the polynomial interpolation. And what we're going to talk about today in celestial mechanics, the Lagrange points. Joseph Louis Lagrange was born Giuseppe Luigi Lagrangia. He was born in Turin, not in France, and that was in the Kingdom of Sardinia at that time. He does, however, have ancestral roots. His great-grandfather was French and was a cavalry officer in the French army. Toward the end of his life, he did become a naturalized citizen of France, but for decades, both Italy and France claimed him and argued over who he belonged to. He was born in 1836, and at age 14, he became a student at the University of Turin. He had no interest in mathematics or science, planned to study law like his father. But his interest in mathematics was sparked when he read a paper by Edmund Halley on optics. And the algebra, not the geometry, is what captivated him. Whoops, went too far, here we go. At age 19, he sent the paper to the greatest living mathematician at the time, Leonhard Euler. And in the paper, he described a new method for finding maximums and minimums of functions. Euler was so impressed that he proposed him for election as a foreign member to the Berlin Academy. And he was elected to the Academy at age 20. In 1764, he won the French Academy of Scientists Award for his description of why we only see one side of the moon and why we observe the libration or the wobbling of the moon in its orbit. 2 years later, he would win the prize again by explaining the orbits of Jupiter's moons. Also in 1766, he succeeded Euler as director of mathematics at the Prussian Academy of Sciences in Berlin. And there he produced several works and won numerous prizes. He published a treatise on analytical mechanics in 1788, and it was said to be the most comprehensive treatment of classical mechanics since Newton. Building on earlier work of Euler, he created the calculus of variance, and he created a new field of mathematics, Lagrangian mechanics, which applied to both solids and fluids. He defined the Lagrangian function, expressing the energy of a system by subtracting the potential energy from the kinetic energy, and that was his equation L equals T minus V. He defined also as part of Lagrangian mechanics a principle of stationary action, that being that objects will take the path of least variation of energy, and thus the partial differentials would be the movement in those directions where you're finding the lowest, least variation of energy. He also defined generalized coordinates, which allows the solution to problems like the double pendulum problem that's on the screen. He standardized notation. He's the person who standardized the use of sigma for summation, the use of a single dot for first order derivatives and two dots for second order. And he standardized the use of the squiggly D for partial differentials. In 1787, he was invited to the French Academy of Sciences, and he left Berlin for Paris. He continued his work. He was offered the presidency of the Commission for the Reform of Weights and Measures, and was instrumental in the decimalization of France. And these are just a couple of the highlights. He had other accolades as well. Almost as remarkable as his scientific accomplishments is the fact that he survived the French Revolution, including the Reign of Terror and the Napoleonic Wars. Others were not as lucky. He was pretty independent of politics. He was quoted as saying, "I believe that in general, one of the first principles of every wise man is to conform strictly to the laws of the country in which he is living, even if they are unreasonable." In October of 1793, there was a decree issued by the revolutionary government ordering all foreigners to leave France. However, Antoine Lavoisier, a French chemist, intervened and was able to convince the officials that Lagrange should be exempt from that decree. Lavoisier was known as the first true chemist and father of chemistry. He has a number of achievements, but he's well known for one of the first modern works in chemistry, including a list of the 33 known elements and their properties, as well as recognizing the role of oxygen in combustion and respiration. However, despite his liberal political views, he was tried and executed in 1794. It is said that his experiment, he asked for a delay in the execution so he could complete some of his experiments, and was told the Republic has no need of scientists. After Lavoisier's execution, Lagrange was quoted as saying, "It required only a moment to sever that head, and perhaps a century will not be sufficient to produce another like it." Quite a telling statement. Now let's look at the Lagrange points. So there are 5 points, and you'll see in the diagram, which shows the contours of the topology of gravitational attraction between the different bodies. Lagrange points arise out of a restricted case of the 3-body problem. And the first thing is they are not points. They are zones or regions of equilibrium. And Lagrange was not the first to define L1, 2, and 3. Euler had defined them back in 1750. But Lagrange was the first one to publish defining all 5 points in 1772. Ever since the work of Newton and Kepler, it was known that it was impossible to solve the 3-body problem. And you can see in the diagram, we challenged to find an equation that would express the location and motion of each of those 3 objects in a 3-dimensional plane. So the approach was to use a restricted case and then iteratively calculate gravitational forces so you could plot where each of the bodies was located. Okay. So the Lagrange points are defined within a restricted version of a 3-body problem, where two of the bodies, for example, the sun and the earth, are much more massive than the third. In fact, the ratio of the mass of the 2 large bodies must be at least 24.96, or approximately 25 times. And the ratio to the third body is much greater. The third body is minuscule in comparison to the other 2 bodies. As an example, the Earth-Sun system, the ratio of masses is 330,000 to 1. And comparatively, the Sun-Jupiter relationship is 1,000 to 1, and the Earth-Moon system is 81 to 1. So each of these systems will have 5 Lagrange points, and they're identified in that in the upper diagram. The lower diagram represents the pair of Pluto and Charon, and their ratio of masses is less than 25. So they would not have any Lagrange points in that system. Also notice that they are rotating around a central point. It's the barycenter of that system. So that comes into play when we talk a little further about the Lagrange points. Okay. So let's start. Picture 2 large objects in space, the Earth and the Sun, or the Earth and the Moon. And first imagine a point between the two where the pull of gravity is in equilibrium. So the L1 point is being tugged at the same amount as the Earth is tugging as the same amount as the Moon. So you can see that L1 is placed between them. That is a saddle point in the topography. Another way to look at this, well, see, one would ask the question, so according to Kepler, if I have an object at L1 and it's rotating in orbit, it would orbit at a faster velocity and a shorter period than, in this case, the Moon would in this diagram. However, with the three bodies in the system, the Moon is always tugging on the object in L1, slowing it down. So it will then essentially rotate around the Earth in the same period and at around the same velocity. Okay. Now imagine a line being drawn between the Earth and the Moon in this case, and extending beyond. So now you could see that there are 2 other positions, L3 and L2. At each of those positions, at L3, for example, you're feeling the combined gravitational force of both of the massive objects. The same thing is true at L2. They're all in line, so the forces are combined. You may ask then, well, why does an object stay at L2 or L3? The whole system is rotating. And so in the rotation, there are 2 effects that come into play. One is the Coriolis effect, and the other is it's a centripetal force that's forcing the object out of the gravitational system. So those points of L3 and L2 are again points of equilibrium, and you can see in the rotating diagram that they're on the saddle of the gravitational topology. Okay. Just want to make sure I don't miss any notes. Okay. So L1, L2, and L3 are on saddle areas of the gravitational plane of the system. Any movement away from the center would cause the object to fly out of the control of the 2 massive bodies. Those points are inherently unstable, and so they require regular and periodic repositioning and adjustment, some course corrections to stay in position. As L4 and 5 are defined, they are along the orbital path of the smaller of the mass of the two massive objects. So they're in the same orbital plane as, let's say, the Earth or the Moon, depending on the system you're looking at. And he determined that the point was at the intersection of the orbital path and the two gravitational forces of the two objects at 60 degrees to the semi-major axis of the ellipse, the orbit. So they form two equilateral triangles. So each angle is 60 degrees, and you can calculate the dimensions from that. So if I look at this diagram on the left, you see that the L2 position in the Earth-Sun system is about 1.5 million kilometers. L1 would be 1.5 million kilometers toward the sun. And L4 and L5 of the Earth-Sun system would be 93 million miles from the sun and from the Earth as the side of that equilateral triangle. L3 would be on the opposite part of the Earth's orbit. So there are different types of orbits that the satellites in the Lagrange points would take. The most common one is the halo orbit, which would be most often occur at the L1, 2, and 3 spots. So the halo, it would orbit in that halo at half the speed of the rotation of the period of the Earth. So for every one orbit of the Earth around the sun, the satellite at L2 would rotate twice in that halo orbit. You could think of it in a way, although the forces are not the same, they're not even comparable. But if anyone's flown a kite, there are certain points when you're letting out the string where the kite will rotate. It'll do a circular roll. So it's similar in that regard when you're in that spot. And so you also need to course correct on a regular basis. On the right side, there are two paths. The oval-shaped one, that is the path of the Webb telescope. And the other one is the Gaia space mission. Okay. So let's talk about objects that occur naturally at these Lagrange points. As we talked about before, L1, 2, and 3 are not stable. So there are no naturally occurring asteroids or objects that would locate at any one of those points. However, there are numerous ones at L4 and L5. In fact, Jupiter has approximately 7,000 and probably more. These are just the ones that have been identified to date. Around 7,000 asteroids that are in L4 and L5 of the Jupiter Sun system. The two areas are referred to, first of all, the asteroids are referred to as Trojans. That was originally the first name given to it because the names of the asteroids were given names of Trojan heroes. And however, today, the convention is that asteroids at L4 are called the Greek camp, and L5 is the Trojan camp. A way to remember that is the Greeks won the war against Troy. and thus they precede Jupiter. They come before Jupiter, and the Trojans trail at L5. L4 in the relationship of Jupiter's orbit comes first. The asteroids in each of the camps, there are two spies, however, and this was because they were named before the convention was adopted to have a Greek camp and a Trojan camp. So you'll see that Hector 624, he is a Trojan hero, however, he's in the Greek camp, and Patroclus 617 is a Greek hero, however, he's in the Trojan camp. So they're alternate. And these are relatively large asteroids. They were one of the first discovered. They're about 110 to 250 kilometers. They were discovered by August Kampf in 1906 and 07. What makes them very interesting is that they are artifacts from the early formation of the solar system. And the Lucy mission, which is underway, its objective, you see the green path on the diagram, its objective is to visit an asteroid in the asteroid belt, and then visit 7 asteroids that are Trojan asteroids, including Patroclus. So here's Patroclus is a binary asteroid system. So here's a artist's interpretation of Lucy visiting Patroclus and Monoetius. So their objective of Lucy is to study the origin of the solar system and the composition of different asteroids, among other experiments. It uses multiple gravity assist maneuvers to slingshot to the asteroid belt and between the Lagrange points in the Jupiter's orbit. There are other Trojan asteroids. The Earth has 2, 2010 TK7 and 2020 XL5, which was recently discovered by Tony Dunn. Venus has 1, Mars 9, Uranus 2, Neptune 22, and they're thought to be captured KBOs, Kuiper Belt objects. And Saturn, interestingly, has none. And the thought there is that Jupiter may have captured them. However, Saturn does have something interesting. There are Trojans of Saturn's moons. So in the Saturn Tethys system, there are 2 Trojans. One is Telesto and the other is Calypso. And I give you the dimensions so you could see the relative difference in the size of each of the objects. And in the Saturn Dione system, there were 2 Trojans also, Helene and Polydeuces. For reference, what you see on the right are the Earth, the Moon, and Dione. Dione is a little less than a third of the size of the Moon, and 12 to 15 times smaller than Earth. So let's look at the paths that the asteroids take. So we'll look at the Earth system Trojan 2010 TK7. They've identified this, they're generally called and classified as a tadpole orbit. And so it takes on that particular shape. It just reaffirms as well, and also understand that this is from the perspective of someone outside of the system, the Earth-Sun system. So it's as if you're looking down at it from outside. On Earth, the orbit would not look like that, nor would it look like that from the sun's perspective. Now, in the Earth-Moon system, there are Trojans as well, but they are part of the Kowalski clouds. And these are two clouds first reported in 1960 and then confirmed in 2018 at L4 and L5 in the Earth-Moon system. Now let's, here we go. Now let's look at some of the man-made objects that are in Lagrange points. So Webb was not the Webb telescope was not the first. At L1, SOHO and the Genesis and LISA Pathfinder, which ended in 2017, they were at L1. And at L2, the WMAP was at L2, and now that's in a solar orbit. Also was the European Space Agency Herschel, the Planck Observatory, the Gaia satellite, and the Webb telescope. For completeness, L3 in the Earth-Moon system would be in the shadow, and you would not be able to communicate or view it from, you would not be able to view the moon from that L3 position. So there are no satellites in that L3 position. So some of the planned missions, European Space Agency has a few, the Euclid, Athena, and Virgil is interesting because it's a combined satellite, one at L1 and one at L5 to study solar weather. LISA, although not using the Lagrange points, I included that there for information because there is a planned or to be planned series of missions for asteroid. The astrodynamical space test of reality using optical devices. And this could be potentially 260 times more sensitive than LISA, using satellites positioned at L3, L4, and L5. So what's been talked about using Lagrange points would be possible missions that could actually help control climate, putting a cloud of debris or reflective material at L1 in the Earth-Sun system would shield the Earth from some of the rays of the sun. You could terraform Venus or attempt to terraform Venus in the same way, putting up a sunblock in that L1 position. One article even talked about putting in a artificial magnetosphere in the L1 position of the Mars-Sun system. But on a more realistic or feasible view, in the Earth-Moon system, L1 has been suggested as a place for a space station for refueling, refueling center, also for a potential lunar elevator, should that technology ever develop, and as a jumping off point for lunar mining. L2 in the Earth-Moon system has been used. China has used it for communication, so they could communicate with objects on the dark side of the moon. And so that would be a use that we would be looking at as well. L4 and L5 have also been talked about as possible places for lunar mining as a way station. But probably the most interesting or exciting to some extent thought about using L4 or 5 is space colonies. So Gerald O'Neill in the 1960s and early 70s proposed building a cylindrical spacecraft that could sit at L4 or L5. And he designed the craft, and it would support a colony of up to 10,000 people. In 1975, the L5 Society was founded, and however, since it has been inactive. However, here we go. Jeff Bezos has a vision. As a matter of fact, in a recent meeting of Blue Origin, he kind of mapped out what he thought he would like to see. So here are some renditions of Bezos's space colony at L4 or L5. You know, he's building a new territory in the shadow of the Earth. It's a great science fiction story, but there are some major problems, as we all know. All right. A couple of the major ones: cosmic radiation. At L4 and L5, there is no protection. So that would have to be incorporated. Long-term space travel, you've got some health issues that need to be addressed. Bone loss due to lack of gravity. And the cost would be prohibitive. Estimating today that the cost of a kilogram of payload into space on the Falcon Heavy rocket is about $1,400. So to build a large cylindrical craft that would house 10,000 people would cost about $5 quadrillion. That's 1,000 trillion. Another way to look at it, it's about 200 to 300 times the total GDP of the United States. And even if you were able to reduce the cost by an order of magnitude, it would still be 20 to 30 times our GDP. Not really feasible. But private space travel goes on, and we have competition between Bezos and Musk. Lagrange died at age 77 in 1813. And during his life, he received many awards and distinctions. Just 2 days before his death, he was awarded by Napoleon with the Grand Cross of the Imperial Order of the Reunion. He is interned in the Pantheon in Paris, and one of 72 prominent French scientists commemorated on a plaque at the Eiffel Tower. Etched on his casket is Joseph Louis Lagrange, Senator, Count of the Empire, Grand Officer of the Legion of Honor, Grand Cross of the Imperial Order of the Reunion, member of the Institute of the Bureau of Longitude, born in Turin, 25 January 1736, and died in Paris, 10 April 1813. Not one mention of any of his scientific accomplishments. I think we can all agree that outside of the scientific community, Lagrange is not a household name and generally unknown, unlike Newton or Galileo or Einstein. However, when you look at his accomplishments, you find that the application of his work extends into the modern world today, a world of finance, game theory, data encryption, computational algorithms, mathematical modeling, and space exploration. We may find that Joseph Louis Lagrange has become a household name on a space colony in L5 in some planet's orbit. These are some of my references. And I want to thank you.
Oh, great. Thank you, Chris.
Thanks, Chris.
Welcome.
Yeah.
Nice. Okay. Does anyone have any questions for Chris about Lagrange or his points?
I do actually. Has there been any talk about? I know you said L3 isn't useful for many things because it's on the other, for instance, like between Earth-Sun system.
Mhm.
But would it possibly be a good idea to have a satellite of, or not a satellite, a probe of some sort looking for near Earth objects, new comets and whatnot that are coming out from the other side of the sun? Like, for instance, Chelyabinsk kind of caught us by surprise because it came from the other side of the sun. It was caught in the sun's glare and we couldn't see it. And then communicating it with it would be pretty difficult unless a second probe was put at one of the other two, like L4, L5, and that would be the communications beacon between the two.
Yeah.
This has, what is that feasible, or has anyone ever talked about that, or is that pie in the sky kind of thing?
Yeah, there was a couple of little articles related to that, and they of course said you would need a relay station.
Right.
And rather than putting the relay station in orbit, because again, you're going to be in the shadow of the sun for a certain period of time and you can't communicate, you should put it at L4 or L5 in
Right.
the Earth-Sun system. So there's some talk about that. But the only thing that I saw using L3 that had some, well-defined benefit was for the laser interferometer, because you could
Right.
have with that distances in that orbit, you've got a lot of sensitivity there, so you
Right.
could detect you could really detect the gravity waves.
Gotcha. Yeah, there's no other large gravitational object in it near region. It'll be the only thing there, essentially.
Yeah.
Right. Gotcha. Thanks, Chris.
You're welcome.
I guess one interesting thing is the Discover satellite is at the L1 point. And if you go on to the Discover website, you get some really nice views of the Earth. You get some really high resolution full Earth images, and they look really nice. And if you time it right, as the moon comes around, you get to see the moon passing in between the satellite, between the L point and the Earth, and it's kind of really cool if you can see that. And the pictures are updated very, very frequently. It's almost live image of the Earth, and so it's really kind of cool to look at.
That's good. Yeah. One other question does come to mind, and I didn't explore it. I didn't want to run too long, but it brings up the question of governance. Once you start putting satellites and you have private people putting satellites up into different orbits or into Lagrange points, how do you control it? How do you govern it? So there are some agencies in the UN that have been chartered to do some of that, but the rules are based more on cooperation, not enforcement. So you could easily have someone who violates the rules or stretches them a little bit. But that would be another mention. Yeah, that would be another topic to cover. Yeah.
Sure. Okay. Any other questions?
Yeah.
Hi, everybody. Can I, Chris? It's thank you for your presentation. It's a really challenging, ambitious topic to present, and you did a good job getting us started on this here. I was wondering if you can give a couple thoughts. The diagrams that you showed, they often have these looping closed shapes that kind of try to give you some sort of three-dimensional sense. And I've never really been able to get a grasp on what's actually being measured or calculated, or what's that a graph of? Showing the loops is nice, And there is some value in that, in the sense that you see the sense of stability centered on L4 and L5, but it's still not, I've never seen a decent explanation of what's actually being graphed there. If that was a three-dimensional shape, what would the axes actually be?
Yeah, it's good question, good point. Yeah, there is something missing there, because this is like, these are contours, almost as if you're looking at contours in the in the earth, on the earth. So you'll have one contour will be 1,000-foot elevation, another one will be 1,100 feet, and so on. But these are contours of gravitational attraction, which is because you have the two gravity wells that they define, whether it be the Sun-Earth system or Earth-Moon system. And so if you fall inward from either L1 or L2, you're going to end up in the Earth gravity well, and you will eventually crash into the Earth, in the absence of any adjustment. If you fall outside, you'll be thrown out of that system. So, but what it doesn't show you, the actual forces working on you on that contour line. The only thing you do know is that at the saddle points, L4 and 5 and 1, 2, and 3, there is some equilibrium there. So that's the only thing you can say. So you don't know what other than the gradient of the contour, you really don't know. You can kind of guess how strong the force is, but you really don't know exactly what direction, because you're moving as well. You're rotating around also. So there are other forces at work. That's a good question. It doesn't.
Yeah, if you don't mind me making another comment, I know you've mentioned a bunch of the different applications here. If you go to the Trans-Astra Corporation's website, they have a proposal for, I think it's called the Sutter Space Survey, and they want to put cluster telescopes in 3 points of the Earth, Moon, Lagrangian, 3 of the points. And as the 3 satellites then do their dance around the Earth system, there will always be 2 of them looking for the Chelyabinsk type impactors that would be coming from behind us out of the sun. And that's why the surveys, other normal surveys, can't pick those up. But the Trans-Astra proposal, which is a private proposal, as far as I know, they're not. They haven't made any applications for any taxpayers' money at this point. But they're optimized for exactly that kind of search. It's really kind of neat. They I don't think I have it at my fingertips, but they've got a video that shows where where the view of these 3 satellites would be, that keeps the over the shoulder incoming asteroids in sight at all times. Yeah.
There were some articles, not from Astra. What was
Trans-Astra?
Trans-Astra.
I'll try and put the link in the chat here. Just give me a second.
Yeah, that wasn't mentioned,
Thank
but
you.
what they did mention was tracking NEOs. So that's one of the uses, or let's say planned usage, for some of the satellites at Lagrange points. So it's a real issue. Yeah. What we do if we found one, I don't know.
What Trans-Astra is hoping to do is, statistically, of course, there'll be more small asteroid objects than large ones. So they're not seriously concerned about wiping out humanity or something like this, because that's such a rare event. But they anticipate that there might be multiple smaller objects in the size of anything from a car to a house, and that there would be a significant amount of water in many of those asteroid type objects. And so they would be worth sending a fairly low energy space mission to actually capture those smaller objects. That's what Transastra's business model sort of is, if I understand it correctly. And yes, Mark, in answer to your question, we do hope to go to AAR this year. And thank you, by the way. I mean, without AAR, I obviously would not have, heard of your group. And thank you for inviting and welcoming. I presume you welcomed all the AAR participants, not just me. If I happen to be the only one on here, that's just my luck. But I presume you extended that invitation to all of us. So thank you.
Yeah, no, we do that quite often. It's just we don't always catch everyone all the time.
Well, I don't mind saying it. I mean, I did notice quite a few of your invitations in the past, and I think this is only my second or third time actually participating online here. And thank you again for making it available that way. But this is one of my favorite topics, the Lagrange points. I've been following this since, Chris, you mentioned the Gerard K. O'Neill proposal. And, you said late 60s. Well, he might have been sort of thinking about it that early, but it was first published in Physics Today. And I think it's the April 1974 issue. And so I was an undergrad at that time, and I was sitting in the lab, and I literally saw the magazine sitting there on the table, because the university had a subscription and someone had left it there.
Right.
And I was just blown away as a 19-year-old undergraduate thinking about this kind of stuff. I've been trying to read about these Lagrange points and how the math works and so on forever. It's totally fascinating and really, really ambitious. So thanks for trying to tackle it here.
Yeah, the mathematics is complex. I wouldn't even try to attempt to parse all of it for you and give you a cogent description. I tried to keep it at a level where you would understand, and certainly I would be able to communicate it, because in one of the articles, this is these saddles are also defined as an intersection of a number of different functions, aside from just the gravitational forces, and it's where they intersect, and so it gets complicated. But thanks for the link. I see it in the chat.
Okay. Any other questions for Chris? Okay.
Chris, you there?
Yes.
Hey, how you doing? Congratulations.
Thank you, John.
I had a thought. Nobody knows about this fellow. I know about him because I help work with you, but you think you should send something maybe to the local French embassy to show of the group's interest in who is uncertain? This guy's an uncertified, undisputed mathematical scientific genius, yet he might as well, nobody ever heard of him. And maybe the French embassy could do something about this to publicize this fellow, because he needs some publicity. I tell you, Isaac Newton, you hear about him, but you never hear about this guy, and this guy's fantastic. I learned a lot about him working with you. He also did a good job in dodging the guillotine too.
Yes, it's very true. Very diplomatic.
Yes, you did. Anyway, great presentation, by the way.
Thank you, John. I appreciate your help. I really do.
No, it was great fun. I learned a lot. Okay, how do I?
Okay. If there are no other comments, I think we should wrap this up, and we should move on to the business part of our meeting here. And so thank you all for joining us. Members, please do stick around for the business meeting. Of course, everyone is welcome to stick around if you like, but thanks for joining us tonight. And I believe for next month, of course, we will be, our meeting will again be on the second Tuesday of the month. and the date escapes me at the moment. Looks like it's May 10th, I believe, is the correct date for that. So our next meeting will be May 10th. And I believe that, are we going to have some student presentations this time for the May meeting, Mary Lou?
Yes, we hope to have student presentations. More on
Right.
that later.
Okay, yeah. So, so student presentations for the May meeting, as we usually do. And so